Hi, we're Group 23, and our project was the LED replacement light bulb for Senior Design 2013. My name's John Foster.
My name is Peter Hashi.
I'm Ian Novara. So these are some of the few things we're going to go over today in our presentation. The first thing we're going to go over is we're going to do an overview of the project design process. Then we're going to do an overview of the engineering requirements. And then we're going to do a preliminary design. And after that, we're going to do a brief explanation of our block diagrams for our project. And then we're going to do a description of the prototype for the design. And then we're going to go over the tested engineering requirements. And then finally, we're going to do a demonstration of the system, and we're going to give our own feedback of the project and our own final and advices for the future students.
This is a overview of the project design process. So here's the problem. You got a standard 40-watt light bulb, plug it in. Unfortunately, it uses about 40 watts. Well, they also don't last that long. They typically last about a year. Then they burn up. You have to buy more. Fills landfills, stuff like that. Super inefficient. Most of the power coming into this bulb is being transferred as heat. And there's just so much better technology out there. So our goal, and another thing is it gets extremely hot. So our goal was to design a light bulb with LED technology. This is just something on the market that uses LED technology to produce light. A lot more efficient. Cooler, much cooler, and a lot last tons longer. Like I think they last at least 10 years. So this is what we wanted to accomplish through the project. That's the basic requirement, was just to reproduce a 40-watt light bulb with LED technology. To make the project a little bit more interesting and give it a little bit more pizzazz, we decided to go ahead and incorporate some infrared or wireless transmission and color changing. So this is what we wanted to duplicate in our project. Just some basic color changing as well as LED technology.
This is the block diagram of our project. Over here we have our main power supply, which is our 12-volt supply. It is a 12-volt 1 amp supply that uses the 120 volt standard outlet. The design itself utilizes a flyback type topology. This power supply then is used to feed our microcontroller power supply and our LEDs themselves. The controller is used to receive IR signals that determine the color and brightness of the LEDs themselves, which goes to the controller then determines a PWM to pulse the drivers themselves, and that's what controls the brightness.
For the engineering requirements, we're gonna go over the way we end up testing our engineering requirements. So for the first one, you can see it's the brightness. So by looking at the graph, you can see the red, that's the original light bulb, which is the 40-watt incandescent, and the blue, that's ours. As you can see, for A and C, those are 45-degree tops, and for B, D, and E, and F those are the flat sides, and G is the bottom. And from the graph, you can see that we almost beat the original LED very much, except for NG. That's just because of the way our LED is shaped like a hexagon, which means that not light is going through the bottom. So for that reason, that's why in the G part, there's not much light going through. So for our second engineering requirement, which was the diameter for the light bulb, So from the just the image here, you can just see that it passes our engineering requirement because of we calculate using the ruler we end up measuring that's around 3.5 inches, but that's just for the engineering requirement. But we also managed to make it up to a 5-inch diameter recess because of that also meets our customer needs. So for the other test, which was the endurance test, so basically for this test we wanted to have the light bulb on for 24 hours. So you can just see here some videos over here that it meets those requirements, and also you can see a graph that shows where the temperature, how it changes, and also for the light, and you can also see how the power there's not really a significant change in comparison to like the temperature, but only to a certain point. Then you can also see that it stays constant after a while.
Okay, so our fourth engineering requirement was LED bulb will be at least 90% of full brightness within 2 seconds of being turned on. Our first bulb kind of did that as well, because as it heated up, the current would go down. This one, same thing with our new prototype, but it's mostly because of the current limiter's inverse thermal coefficient. So as the bulb would heat up, the current would go down, which means the lux output would go down. As you can see in the 24-hour test, lux went down as it heated up. So, and that's just a video explaining the same thing. Omnidirectional check. This was actually checked during the brightness check. Just the same numbers from the spreadsheet that we got. So once we did the calculations, we found out that the average for the 270-degree angles was 82.566, blah, 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 and then the total for the bulb was about 95.9. So 82.56, blah, was about 86% of the total. Our requirement was no more than 30% drop. We only dropped 14%. So that passes. And then our sixth engineering requirement was the bulb will use at most 35 watts. So we just hooked up a regular power meter and plugged in the bulb, at full brightness. When we plugged it in, it ran around 12 watts, anywhere between 11.8 to 12.2. So it definitely met the 35 watt max requirement.
Our next test was the interface check. So we wanted our bulb to make sure it screwed into a standard E26 or E27 socket. For this we done two things. First, we measured it to ensure that it is for the E26 standard, that's 26 millimeters in diameter, and when we measured it, it was 25.9 millimeters, so it met that spec. And also to make sure it was securely in the socket, we shook it at a rate of about 2 hertz to make sure it wouldn't fall out the socket. The next requirement was our temperature test. For that, we wanted to keep the heatsink below 150 degrees Fahrenheit. This test involved us leaving the bulb on full power for 5 minutes, and then taking a temperature reading after or during that 5 minutes, and taking the maximum reading from that. If it was below 150 degrees, it passed, which it did. The next requirement was the weight. For this, it had to be under 2 pounds, which was clearly met by our picture here. We have our bulb weighed on a postage scale, and it only weighed around 6.4 ounces. Our next test was our white colour, which we wanted to be in the range of around 2700 K. For this, we used a control bulb, which is just a standard incandescent light bulb that we knew was in the 2700 K range. For the test itself, we measured the intensity of light through different coloured sheets to measure the intensity of that colour of light against a photoresistor. In this graph here, you can see the photoresistor value through the different colors of sheets. The blue line here represents the standard incandescent light bulb, and the red line represents our LED bulb. As you can see, the shapes are very similar, and then when we normalized our LED bulb using a factor of 2.5, it matched up with the standard incandescent light bulb.
Final design, we try to integrate as much as we could from our previous design, and we threw in the IR control. So when you first turn it on, the white light comes on fully, and then you have your IR controller. Turn it off, turn it on, switch colors. And you can change your dimness. So you can use it as a night light if you want to, or you can use it as a standard light. It's pretty cool. So what's also, it has a memory too, so if you turn down the brightness on green, let's say, and then you can change and it keeps the same brightness. So see, same brightness. Also, you can change colors when it's off. And when you turn it on, you should keep that color. So this is our LED controller section of the bulb. As you can see, we went with a hexagonal shape for the bulb, and all the the white LEDs at least, are around the sides. These are the current limiters, and they're controlling several lines of the white LEDs and the colors. These are the color LEDs up top, so then when the color LEDs turn on, they cover a broad spectrum as well. Yeah. So our power supply has the green solder mask, as you can see, and we included the microcontroller, of course, and some surface mount parts in it to make it a little bit smaller. Alright, so this is the bottom of the power supply board. It has the microcontroller and some of the current limiters for the white lines.
Two main problems. The first was interference with the IR system from the white LEDs. To solve this problem, we'd either have to do it through hardware modifications or software modifications. For hardware, we would just move the IR sensor to somewhere where it got less of the light from the white LEDs, so maybe down here on the case. Or in software, we could change it by just filtering the bits better that the microcontroller is decoding. The second issue was there's still a slight heat issue, and for that we could solve that using technology like these and the newer light bulbs that are out. What they use is they mount the LEDs themselves on actual metal that has traces marked on it with an insulated coating. This dissipates the heat much more efficiently than the PCB boards that we use on our design. And as you can see, they also use a large metal heatsink. And for ours, we could also mount a larger metal heatsink on there to pull more of the heat away from the LEDs.
Here are some of our final thoughts and advice for future seniors next year. So here are some of the things we actually learned this year. And so first of all, we actually learned how to be more independent and also work as a team. And we also end up learning some leadership skills, and as well as communication skills. And so here are some advice for future seniors. a great opportunity. Senior design is basically a great opportunity for you to get involved in your area of interest. So a project that revolves around your area of interest is a good way to start, and also to pick your team members wisely, because you're gonna be depending on them a lot on getting the work done. And finally, budget your time wisely, because you want to do a project that's doable and not over exceed your expectations.